Okay, so it's kind of a mixed bag today. We're going to look at solving trig equations again, and more on identities. I'll also be posting a identity, an identity sheet for you that you can use on your test. And of course, I mean, you can use your notes also, but if you have the sheet handy, then it's kind of all in one area for you, so you can kind of see what that looks like. So so let's just go through a new type of solving question that's maybe a little bit harder than what you have been doing. And so these first ones are when we have a double angle or maybe a triple angle in the question. So let's take a look at 2 sine 2x plus 1 equals 0. And let's say you're being asked to solve between 0 and 2 pi. So you're being asked to solve from 0 to 2 pi. So I'm going to do a little bit of writing just where this bullet is here, this little point here. And you don't have to copy this part down, just sort of see if you agree with this. And so this question is a little bit trickier because when I isolate the sine part, I get sine 2x equals negative 1 over 2. And if I think of a sine curve, it's kind of like that, as a sine curve. And I know the amplitude of this sine would be 1. There's no phase shift up or down here. If I have it isolated like this, that part. But the period of that function is 2 pi divided by 2 because the b value is 2 here. So that would give me a period of pi over 2, 3 pi over 2. Oh, sorry, the half of that, pi over 4. And then right here would be 3 pi over 4. And so why that's tricky is if you look at a negative a half here, so that'd be about there, negative a half, you can see there's 2 solutions on the graph, but that's actually from 0 to pi. If we graph from 0 to 2 pi, we're going to see 2 cycles of this function, which means we're actually going to get 4 solutions to this question. So if we go all the way to 2 pi, because remember that's pi there, that's pi, and that would be 2 pi. So really from 0 to 2 pi, we're going to see 2 sine curves, which means we're going to have 4 different solutions to this question. So what I would encourage you to do for these problems is to do a little let statement here and say let 2x equal a. And so that's going to be sine a equals negative a half. And so I would actually start writing this part down here. I'm going to draw a little line here. The graph just sort of to show there's actually 4 answers here. So steps, if you want to write some steps down, and this is when the angle is not just theta. So right here you can see this is 2x. So you're having a change to the period of the function here. So the steps that I would suggest you do is to, first of all, use a let statement. And that's basically to simplify the question. And what I mean by that is that this new equation I'm writing right here, this sine a here, the period of sine a is 2 pi now, which means that you can solve this just the way we've been solving all the other trig questions now. That is just drawing it on the Cartesian plane. So I'm going to draw my little angle here. I'm going to say, okay, sine is negative in quadrants 3 and 4. So we're looking at an angle here, or maybe an angle over here. I know that's pi. I know that's 3 pi over 2. And when I draw my reference triangles, I know that the y value is going to equal negative 1. It's negative 1. And my r value is going to equal 2. Oh, sorry, negative 1. Negative 1. And the r value is 2. So this actually is a special triangle. This is the 1, 2, root 3 triangle. And it gives us a reference angle in here of across from the 1 is, sorry, opposite the 1 is the 30-degree angle. So that's pi over 6 for my reference angles. So I have a reference angle equal to pi over 6. Holy cow. So that's my first step. It's just trying to find out where I am here, and then I'm going to solve using those rules we talked about before from all the other trig questions, which was sketch your angle, sketch theta, find x, y, and r, find your reference angle, and then of course your reference triangle. And that's kind of what I just did over there. Okay, so really I'm doing what we've done before for many questions in this chapter. And then the third thing I would do, which will be new now, is I'm going to write a general solution. And notice that what I'm solving for here is angle A, which is not really what the question was asking, because the question actually was initially, what is x? Like, what is the x angle? So I'm going to write a general solution for angle A. So I'm going to say angle A1 would be pi plus the reference angle. So pi plus a reference angle of pi over 6. Common denominator is 6's. So 6 pi over 6 plus 1 pi over 6 gives us 7 pi over 6. And that's angle A. And I'm going to say that if I was writing a general solution, then I would want to add whatever it would take to get back to that angle. So that is to make it coterminal. Now notice that for angle A, its period is actually 2 pi. It's the original period, because I switched it here. So what I'm going to say is angle A, a general solution would be 7 pi over 6 plus the period, which would be plus 2 pi n. And then angle A2, angle A2 would be 2 pi minus the reference angle. So 2 pi minus our reference angle. So that would be 2 pi minus pi over 6. Once again, common denominators here are 6's. So this would be 12 pi over 6 minus 1 pi over 6 is 11 pi over 6. And then once again, plus 2 pi n here, where n is an element of the integers. So, so we've written two general solutions for angle A, but once again, angle A is not what we're solving for. We're actually solving for x. So now I have to go back and deal with my let statement. Okay, so that's going to be my fourth step here. So now deal with the substitution. Okay, so angle A is equal to 2x. So down here, I would write angle A is 2x. And that would be 7 pi over 6 plus 2 pi n. And then 2x is equal to 11 pi over 6 plus 2 pi n. And now I divide everything by 2. So if I divide 7 pi over 6 by 2, well, when I divide by 2, I'm really multiplying by half. So 7 pi over 12. And then the period now is also halved. So 2 pi divided by 2 is pi n. And then x2 is 11 pi over 12 plus pi n. So I'm just dividing all the original answers by 2. And the reason for that is that the question, its period was pi. It was half the size of this one. Okay, so the period's different here. So there's my angles x1, x2. But now notice these are general solutions. And the question wasn't wanting to know all the answers. All it wanted to know was the answers between 0 and 2 pi. It's solved between 0 and 2 pi. So what I do now is I go to my general solutions and I just plug in numbers and I try to get all the answers as long as I don't go past 2 pi. So for example, for the first one, I'm going to make n equal to 0. Okay, so that means I would just get 7 pi over 12 plus 0. So the first answer would be 7 pi over 12. But now I'm going to go up by 1, because remember n is an integer. So if I make 7 pi over 12, and I'm going to add 1 pi to that, then I have to add these two numbers together. So if I turn this to a fraction with the same denominator, this would be 12, whoa, this would be 12 pi over 12, and 7 plus 12 is 19 pi over 12. That's one of the answers. This would be another answer. Now I could say, well, let's make n equal to 2, which means I'd be adding another 12 pi to this statement here. And of course, if I do that, I'm going to get 19 plus 12, which is, I'll just sort of show that. So that would be 19 pi over 12 plus another 12 pi over 12, so another period away. And of course, that's going to give me 31 pi over 12. But notice that's more than 2 pi, because I know 24 over 12 would be 2 pi. So that would be too many rotations. So I wouldn't want to do that. Now the other answer, though, I could work with is the other general equation here. I could say, well, let's make n 0 for that equation, which means I'd have 11 pi over 12 plus 0. So I get 11 pi over 12. And then I could do another equation, which would be 11 pi over 12 plus 1 pi, which is 12 pi over 12. And that gives us 23 pi over 12. Notice that's almost 2 pi, like you're almost past your 2 pi. So if I added another period here, I would be past 2 pi. So notice how I got 1, 2, 3, 4 different solutions. And you can see that from the graph, there should have been 1, 2, 3, 4 different solutions. So these questions are a little bit trickier, but I think if you follow these steps, they'll work out quite nicely for you. And I'm going to do another video about this. So if that was a bit quick, maybe that I went too fast on that. I'm going to do another video that's going to be a bit more detailed for you. So so this is where you have angles that are not just theta in here. So you've got maybe a 2x or a 3x or some other number in there. And I would really encourage you to use a let statement and simplify the question down so that it becomes a question that you've done previously. Okay, so the other solving question I wanted to do here is not quite as nasty as that one, but it actually might seem a bit strange at first just because of the way the numbers are here. So let's just call this example 2. And I'm going to write this as sine theta equals negative 0.352 3. Okay. Now this question, you'll notice that this decimal number doesn't look like anything you probably would remember in terms of being special. So what I mean by that is it doesn't look like a √3 over 2, or you know, like maybe a 1/2, or some other ratio that deals with those special triangles we were talking about here. But it still is a sign question, so you could be asked to solve for theta. Okay, and what I would maybe encourage you to do here is once again follow those rules we've been using for all the solving questions. So sketch your angle, find your x, y's, and r's if you can, and then you know, basically solve the triangles that are there. So we've got ourselves a negative sign here. So we know that sine is negative in quadrants. Well, what's that rule? What's that rule we taught ourselves? ASTC. So we got a negative sign there. So that means we must be in quadrants 2, 3, and 4. So I'm thinking quadrant 3 and quadrant 4. Okay, so I got to be somewhere over here and somewhere right here. Okay, and then I'm going to draw my reference triangles. And I try to find my reference angle, because once I know my reference angle, it's going to be pretty easy for me here. I know that's pi. I know that's 2 pi, 3 pi over 4. And so what do I know about the numbers, I guess? Like, once again, this is not special here. I'm not seeing like a √3 and a 2 and a 1 here. Let's put this over 1 though, because as a fraction, that's what it would be over 1. And so this is y over r. So I know my y value is negative 0.3523, and my r value is 1. And my x is, I don't know what my x is. I have to figure that out. But I don't know if I need to figure that out for this question. So let's just write that on the diagram. Negative 0.3523, negative 0.3523. That's why you're in quadrants 3 and 4, and a radius of 1. So this could be the unit circle, really, because the radius is 1 here. Okay, so how do we solve for theta? We're trying to find the angle theta here. And so what I'm going to do is, once again, find my reference angle. So I'm going to find my reference angle. And the easiest way to do that, well, the only way to do that is to use your calculator. So I'm going to draw a triangle. And I'm going to try to find this red dot right there. It's 90. And this is where that's a 1. And this is 0.3523. Now notice that I've made this a positive number. And the reason for that is I already know where the triangles are. I know the negative told me they were in quadrants 3 and 4. So since I know that, I don't really need to include that anymore, because I'm just going to find out what the reference angle is here. So in order to get this dot here, to find out what that is, you have to undo the sign. So to do that, you go second function sine, and you input positive 0.3523. So I want you guys to use your calculators and do that. I want you to see what you get there. But make sure you're in radian mode, because we're solving this in radians. So just take 30 seconds and you guys crunch the numbers on your calculator and see what you get for a value. Okay, so this is an irrational number, so it just goes on forever. But I'm getting 0.3600. So what is that? What is that? Well, that's actually the angle in radians. If you used your calculator in degrees, you would have got a larger number. In fact, I can do that pretty quickly here. Let's go d. So let's go second function sine, 0.3523. So and if you're working in degrees, I would have gotten 20.6 degrees roughly. So that means the reference angle is 20.6 degrees. But let's stay in radians here. That means this angle here is approximately 36 radians. And this angle over here is about 0.36 radians. Okay. So now we need to find out the first angle. So the first angle would have been that angle there. Let's call it angle A1. Okay. So angle, I should call it, I use theta. So let's use theta. Let's call it theta 1. Okay. So the first angle theta would equal pi plus the reference angle, because notice you're in quadrant number 3. So if we do that, we take pi and we add that number to it. So I'm going to add pi. I get 3.502 radians. And to find the second angle, I do 2 pi minus the reference angle. So I'm going to go 2 pi minus a reference angle of 0.36. And so I'm getting 5.92. 3, I guess, if I go to 3 digits. So there's my two angles in radians. Now, you might remember the last test question we did. There was a question where you were trying to find like the height of an object on a wheel. And you have to kind of convert into radians. And sometimes you get these nasty numbers, and they're not nice values to work with here. So this actually is on page, I'm not sure if you have your book handy or not, but page 322. And it's question number 2. And so I would try, you know, maybe pick 4 or 5 of those, give them a try. I'm going to probably just have 1 or 2 questions on your next test dealing with these kind of ugly numbers. So if you are kind of not getting it, if it's a bit trickier, I will be posting another video on this, but it's also not going to be a big part of the next test. So you don't lose too much sleep over it. But that's if you're not dealing with special angles. And of course, in the real world, not everything's nice and tidy. And sometimes we have to be able to manipulate questions where the numbers aren't special for us. Okay, so once again, I told you it's going to be kind of a mixed bag of things today. So I'm just looking at the time; it's 2:30 almost. So the last thing I wanted to sort of spend a bit more time on is the other identities. Oops, identities. So I'm just going to pause for a second here. Does anyone want to ask anything or have any questions? Or have you guys just like, are you guys playing video games right now and just pretending to be here? I know Lauren, she likes playing video games. Okay, so let's move on then. So let's take a look. So if you guys want to ask a question, please feel free to. Now, if you go to section, if you do have your book handy, you can kind of follow along with me here. If you go to section 7.5, 7.4 actually, let's do that first. 7.4 really kind of gets into the scariness of things, and they actually derive or come up with like how these identities came about. So I'm not going to be holding you guys accountable for that. I would say if you're going into an area like mathematics at university or physics, and even calculus engineering type courses, you really should look through the proofs on this. But just because of time and how challenging these proofs are, I'm not going to be covering them in the lessons. They take too long to go through. But what I would like you to know is that on your identity sheet, you're going to get these identities given to you, but I think it's worthwhile showing you them now. And that is the addition identities first. So sine A plus B, sine A minus B, cos A plus B, and cos A minus B. And so basically, you can see we're adding or subtracting 2 angles, and we're using a trig term to do that. And so these identities are true statements in math. So the same way that you probably remember sine squared theta plus cos squared theta equals 1. That's just a type of identity called a Pythagorean identity. These are called addition identities. And so the sine one goes sine A cos B plus cos A sine B. And then the next one is sine A cos B subtract cos A sine B. And then the cos ones are, they're a little different. They both start with coses, so it's cos A cos B. Now when it's an addition for cos, it's actually subtraction here. Sine A sine B and cos A cos B plus sine A sine B. Now, once again, you're going to be given these identities, so it's not a matter of you trying to memorize them. It's more how you use them, like what kind of questions you would use them in. There's also a tan identity that I'm not going to cover. I do cover that, but just once again, because of time and difficulty, I don't want to overload you guys too much. But those are some of the identities, and this is on page 328. And if you actually look at the bottom of page 328, you'll see these identities called the even, odd identities. And once again, I would say if you're going into engineering or computer science, you should learn those. Like you should memorize those actually. That's just part of the language they use in those courses. But because of our time, I'm not going to be going through them. And the other reason is you can actually get those by using the 4 identities I just showed you here. I'm going to show you an example of this, just because this kind of question could appear on a test. So I might say to you, what does sine pi over 2 minus a equal? And if you're looking at page 328, you're going to see that it equals cos of a. Now, what I want you to be able to do is not memorize that, but to see it and how you would actually determine that it equals cos a. So in a multiple choice question, I might give you this statement, and then you might have like a, b is sine a, c is tan a, and d is the log of a tree. There's usually like one stupid answer on the test, right? So we have these 4 answers. So the question would be, which answer is it? And once again, if you want to memorize it, that's fine. But if you just know these identities, then you can actually easily get this answer pretty quickly. So I'm going to look at which identity of the 4. So let's call this 1, 2, 3, and 4. Which of those 4 identities does this one closely match? And so you can see it starts with sine. So I'm thinking it's got to be 1 or 2, right? And I notice there's a subtraction sign between the pi over 2 and the a, which means it has to be number 2. And so what I'm going to do is I'm going to write out this identity in long form. And now I got to remember that this is a, and I'm minusing b. That makes sense. I'm looking at a minus b. So I go sine a cos b. So sine pi over 2 cos a minus cos pi over 2 sine of a. Probably should have picked a different letter, but oh well. Okay, so here we go. So we got sine pi over 2 cos a minus cos pi over 2 sine of a. So once again, does not look a lot like any one of these right now. Right, this looks quite different here. But you should remember that pi over 2 is special. It's a special angle. And so if I'm thinking about shapes, I think my circle here, I draw my line. Well, where is pi over 2? Well, pi over 2 is right at the top here. And that's the coordinate 0, 1. So I know my x value is 0, my y value is 1, and my r value would be 1 on the unit circle. So what is the sine of pi over 2 then? Well, the sine of pi over 2, just going to draw an arrow here. The sine of pi over 2, well, that would be y over r. So that's 1 over 1. And I'm timesing that by the cos of a. I don't know what that is. Now I'm minusing the cos of pi over 2. Well, the cos of pi over 2 is 0 over 1 times the sine of a. So I have 1 times cos a, which is cos a. And then I have 0 times whatever is 0. So this does equal cos a. So that's one way you could get that identity without memorizing the even odd identities. And so I would say it's not really worth your time to memorize those unless you're going into engineering or maybe computer science. Okay, so let's try one very similar to that and see how you guys fare on that one. So why don't you guys try this one on your own? And once again, I'll scroll up so you can kind of see those 4 identities. Hopefully you can see that. You might want to write them down because I'm gonna scroll here and you won't be able to see them. But let's say you had the cos of let's say q plus 3 pi over 2. And I want you to determine what that equals in terms of, is that going to give us cos q, sine q, negative cos q, or negative sine q? So try to expand that with the appropriate identity and then see if you can simplify it. Okay, so this is the addition identity for cos. It's cos A plus B. And really in place of A, I have a Q. And in place of B, I have a 3 pi over 2. So I'm going to change that right here. I'm going to just erase those. I'm going to plug in those numbers. That's Q. That was Q. And that's 3 pi over 2 and 3 pi over 2. Okay. So, well, I need to know where 3 pi over 2 is. Let's use the diagram we just used there. So that's 3 pi over 2. So in the unit circle, that's 0, comma, -1. So I know my x value will be 0, my y value will be -1, and my r value would equal 1. So the cos of q is just the cos of q. I don't know what that is. But this cos of 3 pi over 2, that would be x over r. So that's just 1. Oh, sorry, 0 over 1, which is really 0. Minusing the sine of q multiplied by the sine of 3 pi over 2, which is -1 over 1. So this is just 0 over there. And now you have subtract sine q times -1. So the negative turns the negative into a positive. So really it's plus the sine of q. So the correct answer would have been the sine of q. If you're more of a graphing student, you might have realized that this is also a translation of the cos graph. So you're moving at 3 pi over 2. And if you did that to the cos graph, you actually would get the sine graph if you did that. But it's hard to kind of see that, I think, so in this chapter. Okay, so there's 3 identities, 3 addition identities, or sorry, 4 addition identities, the sine and the cos. And once again, if you are going into more higher level mathematic type courses, I really would encourage you to look over the even odd and cofunctional identities, and that for tangent also. And then the other identities I want you to be aware of are in section 7.5. And there's once again a lot of identities here. There's just 2 that I want you to focus in on. And that is the double angle identities. For sine and for sine and for cosine. So the sine one's actually quite easy. I think it's quite easy to get. And once again, there is a derivation for this. That means like there's a way to sort of show why this equals what it does, but I'm skipping that. But you can easily look that up in the book. It's actually quite well explained. Sine 2a is equal to 2 sine a cos a, and then the cos of 2a is equal to, now this one's a little bit tricky to remember. And even if you have your data sheet in front of you, like the formula sheet in front of you, it's really easy to get this mixed up even with that in front of you. And so it's actually cos squared a subtract sine squared a. And you've actually seen something that looks a lot like that, and this is why I think why you can easily get confused with this one, is that looks a lot like the Pythagorean identity. The difference is though, the Pythagorean identity is cos squared a plus sine squared a, and that's what equals 1. So trying not to get those confused, that little subtraction sign there does make quite a difference between the 2 answers. Now you might remember that we wrote this one in 2 different ways. We wrote it as 1 minus sine squared a equaled cos squared a, and 1 minus cos squared a equals sine squared a. So you might remember we sort of showed that and said sometimes it's better to know it that way. And the same is true for this one. Cos 2a can be written in 2 other variations. And they're just, the reason we show you this is it helps sometimes to know the other variation. So if you replace cos squared a, so cos squared a with 1 minus sine squared a, then you actually get 1 minus 2 sine squared a. And if you replace the sine squared a's with sine squared a, then you get a 1 minus cos squared a in there. But you're subtracting that 1 minus cos squared a. And so what that gives you is 2, should I use the same color? You get 2 cos squared a minus 1. Okay, so that's I'm cramming stuff in here. Now, once again, I'm going to be doing other videos that it's going to go a little slower through this, but I thought since you're here again now, I might as well just show you everything we're doing in the chapter. And so then we can say we're done. And over the next few days, we're just kind of just sort of working our way through these different identities. So I'm going to kind of scroll around here a little bit. Okay, so in blue, there's the double angle identities. And at the top, here are your addition identities for, for sine and for cosine. So, so really today I'm showing you 6 identities, so 6 new identities, but there's actually even more than that. And once again, it depends on what you're going to study. If you guys turn to page, oh, where are they? Yeah, page 339. So page 339. You'll see down there what they call the power reducing identities, and we are definitely not studying those. I don't normally teach those anyway, but it just shows you there's so many different identities out there, so many different rules. And if you're going into post-secondary classes that involve this kind of math, then knowing those identities is going to really make you sort of have a leg up on other students that don't know those. But just the way the time's going right now, I don't feel comfortable covering all these different identities. So I'm keeping it pretty small in what we're doing. So today we learned 6 new identities. And in previous videos, we learned about, I think, 7 or 8 other identities. So that's kind of about it that you need to know to get through the questions I'm going to ask you. And then right now in the last 10, 15 minutes, I'm going to go through some examples of how to use these identities. So if you could just give yourself a minute, and if you could have on a separate sheet of paper the 6 that I've taught you today. So have those available so you can see them, because you can see it's going to be hard for me to kind of keep scrolling up and then down, up and down. People are going to get really frustrated. So if you could have these 4 and these 2, sorry, these 2 here, handy, so that whenever we're working through it, I can just say, oh, that's the double identity for sine, or that's the addition identity for cos, and it's right in front of you so you can see it. So just take a minute to get yourself organized, and then we'll kind of go through some questions here. Okay. And now, and also the thing is, even if we were in class and everything was normal and I was teaching you this, really what we get you to do in this part of the course is just recognize this is an identity what I'm about to show you, and not really show you like the application of it. So last chapter we did like Ferris wheel questions. We were like asking you how high above the ground an object was. We don't do any of that in this chapter. It's just purely which identity am I talking about. So let's see, if you look at the 6, have them in front of you, see which one you think this is. So see which one you think this is. So example number 1, let's go cos pi over 8, cos 7 pi over 8, plus sine pi over 8, and sine 7 pi over 8. So take a second to look at your, oh, can I let Kyle, is Kyle waiting? Sorry. Sorry, David, is Kyle still there? I was looking, I didn't see him. Tell Kyle I'm sorry. I didn't see him on the list there. I was looking, but I didn't see him on the waiting list. So okay. So which identity do we, David, what do you think? Which identity do you think this is? David's said something, so does it look like any of them? Okay, well, Well, I'm adding some stuff here. So I've got cos, cos, sine, sine. So this looks like a lot of crazy stuff, right, guys? Cos A, cos B plus sine A, sine B. And that's the one of the addition identities. But this actually gives us cos A minus B. So I'm gonna shorthand this to cos A minus B, where A is pi over 8. And now I'm minusing 7 pi over 8. And so that's going to give me cos of 1 minus 7, which is negative 6 pi over 8. And if I reduce that down, I get cos of negative 3 pi over 4. And now I got to be careful here because I've seen that ratio before, that pi over 4 business. That's a 45-degree angle of some kind. So I'm going to sketch this thing. So that's pi, and that's 2 pi. And if I'm looking at the angle negative 3 pi over 4, that would be that angle. And that gives me a reference angle of pi over 4. And so that makes this the 1, 1, root 2 triangle. So this is negative 1, root 2. So I know x is negative 1, y is negative 1, and r is root 2. So this actually would be x over r. So negative 1 over root 2, which if we rationalize that, we get negative root 2 over 2. So this first part up to about here, that there, that's just you recognizing the identity and basically simplifying the equation. And then the second part, oh my goodness, the second part is using some basic trigonometry to find out what the ratio is of that angle. So I'll just do maybe just do 2 more here. Just kind of, I'm sort of throwing everything out at once. Let's do a proof here. And we'll do a proof of an addition identity. So we're going to prove, actually there's just one O there. Prove that sine A plus B minus sine A minus B. We're going to try to prove that that is equal to 2 sine B cos of A. Okay, so we're going to try to prove that that is true. I'll just draw a little line down the middle. Okay, so when I try to prove this, I need to pick a side first. So I need to pick a side to work with. And to me, it looks like there's more stuff on the left side, so I'm going to work with that side. Now, I should recognize that this here, oopsie, and this here are 2 separate identities. And so I want to look at my formula sheet, and I want to see what is the identity for sine A plus B. So you want to look back on your notes and check out what that is. And that's the addition one. So that's where you go sine A cos B plus sine, or you said cos A, sorry, sine B. I'm just going to flip up to show that. So that's sine A, right? So back down the bottom. There we go. And now I'm subtracting. So I'm subtracting this identity. So I'm gonna put this in brackets here. And this is the subtraction identity for sine. So it's the same, sine A cos B, but now minus cos A sine B. Just gonna squeak that in there. Okay, so let's drop that set of brackets. So sine A cos B plus cos A sine B minus sine A cos B, but then that negative turns the other negative to a plus cos A sine B. And you'll notice that two of these terms are going to cancel. Sine A cos B will cancel with negative sine A cos B. And I've got one of those and one of those, so I have two of those. So I have 2 cos A cos, 2 cos A multiplied by the sine of angle B. And of course, this is the same thing. It's just arranged differently. 2 cos A sine of B. So really what you're doing is just recognizing identities in this chapter. Okay, one last question, and then we'll call it quits. I can do this in 5 minutes. So let's take one last example. Another proving question. Let's prove one more here. Something doesn't look too crazy. Yeah, let's go. Okay, so let's prove that sine 6x all over 1 plus cos 6x is equal to tan 3x. Okay. So I'm going to try to prove that is true. So we kind of have to assume it is true, otherwise it's not provable. So I'm just going to double check I wrote it correctly. So sine 6x all over 1 plus cos 6x equals tan 3x. So once again, we're going to pick a side. I'm going to pick the left side. There's more things there, so I'm going to work with the more things side. And now I want to kind of think about identities here. So I noticed that in these trig terms, I've got this side having a 6x and this side having a 3x. So if I'm going to change this left side into the right side, I got to somehow deal with that. I got to somehow make that 6 into a 3, which really has to do with my double angle identities. So there's my two identities there. So for the numerator of the fraction, I can do that pretty easy. But I have to realize I'm not going from 2a to a, I'm going from 6x. And I notice that when I do that, basically I go from 2 to 1. So I divide it by 2, which is going to work nicely for me here. So sine 6x should become 2 sine 3x cos 3x. So notice that this number gets halved into those numbers. So this top here becomes 2 sine 3x cos 3x all over 1 plus. Now, you could just jump and use that identity if you want, but I always try to think ahead here, and what I really want to do is get rid of that 1. Like that 1 is a pain because it's not on this side, so I want to get rid of that 1. So it'd be really nice if I could use an identity that makes me subtract 1. And so if I go back to the top, or not the top, but up here, there we go. You might remember that we said that the cos can be written this way, or this way, or that way. And I'm liking the last one a lot because you'll see there's this minus 1 on the end of it, which is going to allow me to get rid of that 1. So I might try to jump and do that. So let's see if I can go back and use this. So let's draw a line here. And let's say you've got cos 2a. That should equal 2 cos squared a minus 1. How do I do that if it's not cos 2a? Because in this case, it's cos 6a, or case 6x here, okay? So Well, it looks like when I go over, I'm gonna have a 2. I'm gonna get a cos squared, and then I don't get x here because I need to divide the 6 by 2. So I'm gonna get a 3x minus 1. So I have 1 plus 2 cos squared 3x minus 1. So 2 sine 3x cos 3x all over. Now the ones are going to cancel. And now down here, downstairs, I'm going to get 2 cos squared 3x. Now remember, I'm trying to go to tan 3x. So what I might do here, let's turn the tan into sine 3x over cos 3x, just to sort of see where I'm trying to get to here. So it looks like I'm pretty much there. I just got to get rid of a few things. So I know the 2's are going to cancel. They're going to go away. And I know I've got 2 coses on the bottom, so I'm going to get rid of one of those coses, and that would leave me with just 1 there. So I should, because I've done a lot of crossing off here, I should write down the final statement, which is sine 3x all over cos 3x. Okay, so today was a big day of like everything, but we're actually finished now. And then the next couple of videos I'm going to do are going to be sort of rehashing these 2 topics and sort of going through different examples of how to use the different identities here. So I'm just going to unshare this here, and I'm going to turn off my recording.